So in this section 10.5, we are going to formalize some of the concepts that we've been working with algebraically, graphically, and numerically, talking about limits. This is sort of going to be our transition into calculus directly. And then in chapter 11, we will learn some more straightforward techniques that have been built because of what we do with this foundation. So 10.5 and then 10.6, we get into an algebraic calculations to be able to sort of use limits to prove what we're doing. And then when we get into 11.1, we start getting some techniques that are going to be easier to do and get the derivative. And we're going to today talk specifically what is the derivative. We're going to give a definition, and we're going to take both the graphical and numerical viewpoint in this section. Again, following up just like we've done with our other sections, finishing with an algebraic view of the derivative. So 10.5 and 10.6 will go together very nicely. We'll start by taking a look at an example from 10.4. We had this equation here, G of t, and what it was giving us is the price of gold, spot gold at a particular time, a particular month, actually. So what we could do is the difference equation helped us work towards an idea of getting, the goal was we want to see what was the change in the price at the 8th month. That's what 8 represents. And so what we did is, since algebra only gives us techniques to take rate of change between 2 points, slope, right? So we took the point 8 and a little bit more. H was +1, as we see from this table. So H became 1.1. And what we did is by making H smaller, we were making the distance between those 2 points, starting with 8 to 9, getting that slope. That slope was actually 0. There was no change over that time period. But as we made that change smaller and smaller, the rate of change from the difference quotient approached -$5 per hour. So what does that mean? Well, again, taking this as we got the limit, as we got very, very close to 8, so 0.0001, just a 10,000th away from 8, we saw that the instantaneous rate of change, that's what we're going to call it, is -5, because that's what it is. At that instant that we had that piece of data, the change is that the price of gold was dropping by $5 per hour. I guess these were, wasn't months, it was hours. So the 8th hour. Okay. And we're going to further develop this. So that was our example. And so now we're going to talk about what is instantaneous rate of change. Well, it's the rate of change at a point. So rate of change we thought of from a secant line, which we'll define a little bit more, was from 2 points. And as we used limit to make the distance between those 2 points go down to 0, we have instantaneous rate of change at this instant. So this is the feeling if you're in a car that has a big engine that takes off when it goes real fast. That's that feeling. That's that instantaneous rate of change. Or if you have to stop real quickly, that's the other feeling that's not so pleasant of instantaneous rate of change happening very quickly. Okay, so we use this, this is for our notation. What we use is F prime. There's a little prime up there. It's kind of like a apostrophe. In math, we call that F prime. And that will denote the instantaneous rate of change. Okay, it is what we're also going to call the derivative. So we see that over here. It's one way of making the derivative. We're going to see some other notation that gets used, but we'll introduce that a little bit later. We're just going to now use the prime. F prime is the derivative. So the quantity F prime is the derivative of the function F. So we have two things. We have kind of the function, and then we have its derivative which is the slope at any given point. It's a separate function unto itself. And we'll see those connections as we move forward. So we'll say we're differentiating at f. So we're differentiating a function, we're getting its derivative. So there's two things that are important that are needed for there to be a derivative. First of all, we have to use an interior point. So we've been talking a lot about over an interval with the endpoints, and we've been using that as a secant to get an average rate of change with the endpoints. When we get to instantaneous rate of change, we need to use interior points, not the endpoints. We can't take the derivative at an endpoint because of some of the technicalities of it. We need to have continuity. There's some things we can't check that are happening at that point, at the endpoint. Okay, and also that this limit has to exist. This difference quotient, as we basically start with 2 points and we move towards that one, that limit has to exist. And so we're going to develop that a little bit further, okay, by some examples. So the technical sides of things, what we're going to do is the green is our function, f of x. And what we've been doing when we take average rate of change is we've been getting the secant line. So we choose a and then some point a plus h, a little distance from a. So we get 2 points on the function, and we are able to get the x values, which are down here, and then the y values, which are the function values from the green graph in this sense. Okay. What we're doing now is as we look for instantaneous rate of change, we have moved this h, the distance between the 2 points, we made it smaller and smaller and smaller until we get it down to 0. And then what we have is a tangent line which goes through the graph at one point. Now I say at one point, it's tangent at one point. We're getting the slope at one point. Now you'll see back here, the function is going down. And so this is going here. It's going to intersect this function someplace over here, most likely, unless something else happens. And we'll look at that example. That's okay for a tangent line. We're still, because we're focused on this point here, that it locally is just passing through one point, the point A. That's a tangent line. Okay. So here's a couple other examples that a tangent line potentially could intersect in two places, but we're really not using this this second intersection point Q because of the way it is. We're focusing that at P, it's only that place of the graph, it's only going through that single point. Okay, we're not, Q in this instant is not important to us. We're not trying to get the secant line, although again we could use that as an aid, but what we're looking at is we just need the slope of this, that this is a tangent line. And over here, here's maybe more what we think of as a tangent line. So sometimes a tangent line can actually pass through a graph, not just touch and what we really think of tangent on a circle, just touching at one point but not going through it. So tangent lines have various things, but the important part we're going to focus on, it's a place, a tangent line is a place where goes through the graph at one place of importance. And if it happens to do it in a secondary place, that was just because the graph curved and got back in the way. Okay. And what we want to focus on when we're focusing on the derivative, remember that's instantaneous rate of change. It's at this moment in time, not in the future, not in the past. And what happens is as we focus closer and closer, we zoom in on that point of tangency, we start to see that whatever that graph is, no matter how curvy it is, the closer we zoom in, the straighter it starts to appear. And at that instant, that function graph is almost linear. And we take this part of mathematics, which is true. If we go in close enough, one point to that, we get straight lines. Okay, so that's why the line is so important in our mathematics. It's really what we're using here in this calculus. But it only solves problems in this instant. Now, some very curvy lines, the instant may be very short. functions that are a little bit closer to being linear at that point, at least, the predictions that we're able to arrive at may have a longer shelf life, as we say. So they might be a good prediction for a month, or they might only be good for a day, or an hour, or a minute or two. Okay, so it all depends upon, as we zoom in, how long that graph actually sticks towards that instantaneous rate of change. Okay. So that's the overall picture of why we use it and why it's so important in business, is because this is the mathematics that's going to not just tell us what we did, but take what we did, our data, take where we are, and try to give us a prediction of where we're going into the future. Okay, so I'm going to look at a few examples here. And this first one, we have the function's represented by the blue line. We have a tangent line, a point of tangency right here. Okay, what we can do is to find the derivative at this point when x is 2, what we need to do is just find the slope of the tangent line. And we can do that graphically by various means, but basically we just need to find 2 points. And it looks like we've got this nice point here, 1, 0. And I can see another nice point up here. Now there's others. We've got 2, 5. We could have used that one. So we rise 1, 2, 3, a run of 1. Oh, sorry, here. Yeah. That would be 2, 5. This is 1, 0. It's just interesting. No. Sorry. I've got to watch. They fooled me. They should have a little thing down here. This is not going to 0. It's a y value of 2. Sorry. So it's 1, 2. They've zoomed in the graph. So be careful on that. It got me. It could get you too. Okay, so we'll use the point 1, 2. And another point I see up here is 3, 8. Remember, we just need to find the slope, so that ancient Indian technique, we could just subtract the 2 points. So 3 minus 1, well, that's -2. Since 8's in the bottom, 8 minus 2, that's going to be 6, but it'll be a -6. And then remember, just take this x rate of, or x change, tuck it underneath. That's the change in the y's over the change in the x's, which gives us a +3. And we can see that that's what was throwing me off. I got a rise 1, 2, 3, a rise of 3, a run of 1, a rise of 3, a run of 1. So what we say is for this function, call it f of x, right? This blue function f of x, its derivative, the derivative at the point 3, so the derivative at 3, not 3, at 2. I'm getting confused again. The derivative at 2 is equal to 3. 3 is the slope of this tangent line. Hope I didn't confuse you, but we'll look at some more examples in this. But once we have a tangent line, we can use that tangent line to find the derivative at the point of tangency. Okay. So let's clear off the screen, and then we'll move forward. So some quick ways to approximate the derivative. We can use the difference quotient, and we saw that we calculated several of these. We've been doing this just to show ourselves at the limit as this approaches a certain number. So we always found that when we made it h a very, very small value, that limit, that would give us the limit. We'd get as close as we needed to. So one way, just use the difference quotient and plug in 0.00001. Okay, that'll give you a quick approximation. Now, there is another formula we could use because what's happening here is we're using, Okay, up here we're using some point A, and then we're using A plus H, and we're getting closer to A from one side. Now the other way is we can use a balance approach, which is a little bit more accurate, because what we're doing is we're using the point A, but we're looking at 2 points on either side, one where we add H and the other one where we subtract H. And as we make H smaller, we're moving these 2 points closer to that 1 point. So we're coming from both sides. You gain a little bit more accuracy. Sometimes it won't make a difference, but what's interesting that I found, that this comes right from the text, that this is one of the methods used by calculators. So it may appear that they're doing it graphically or some way, but what they're doing is they're just taking the function you plug in, and it's got this as a built-in function to find its derivative. So we'll take advantage of that as well. Okay, there is a function inside the calculators that will actually calculate the derivative at a point, the numerical derivative at a point. And what it's using is, at least what we believe it's probably using for most calculators, many calculators, it's using this balance difference quotient. It's got mathematics embedded in it. Okay, so let's clear that and move on to the next one. So here's an example. So we're going to, in this example, look at that we have a position function. When we take its derivative, we get the position over time, right? The derivative at any one point of this is, the units are going to be, again, this is a ball that is s feet high, t is in seconds, so you have feet per second would be the rate of change, would be the rate we get from any rate of change or instantaneous rate of change. So first of all, to calculate the average velocity, what we need to do is average velocity between 2 and 3 is we are going to need, let me get my pencil back. So we're going to need to take this point and this point. Okay, so we can't really read them from the graph, but we do have a function here where we can calculate them. Okay, so what we're going to want is f of 3, that's the y value at 3, minus f of 2. You'll see from our early example that is going to be a secant point, a secant line. So its slope is going to be an average rate of change. And the x value is in the denominator, 3 minus 2. So what we're going to want to do is we'll put this function into our calculator. We'll have the table tell us what f of 3 is and what f of 2 is. And I just need to find a TI calculator. And again, this one is, the emulator is available with a 90-day free trial. And so I'm taking advantage of that. It's about $140 when if you decide to keep it beyond that. I still have 86 days left in my trial, so I'm going to use it for a while here. And so what I need to do is I need to bring it over here where you can see it. Okay. There we are. I'll get it where it's a little clear. So I'm going to go to y equals. That's where I'm going to put in the function. I'm going to remove this. This is for something we did before. Instead of removing this completely, because we might want to use that later, I'm going to enter on it, and then now it's not selected, so it won't be used by the system. Okay, so I want to put in 100, set formula 100x minus 16 x squared. I think it's the constant, the pull of gravity is 16 feet per second. I think that's where the 16 comes from. Anyone into physics, you'll be able to check me on that. But you'll see the 16 a lot in these. So we're throwing the ball straight up, trying to make it go as fast as we want. You can look at the book's example here. And then what I want to do is I want to go to the table. So I'm going to go to my table set first, starting at 0, increasing by 1. Actually, it's on ask. I'm going to change it to auto just to give me the values I want. And then I'm going to go to table, which is blue. So I go second table. And when I get working through some of the examples, I'll use the Casio calculator as well. I'm just not proficient enough. I apologize for going back and forth between the two types of calculators. But let me know if you're interested in the Casio. I will get it done for you. Okay, so after 2 seconds, we're at 136. So that's the Y value. And 3 seconds is 156. So I'm going to move this off a little bit so I can write in my values. So f of 3 is 156. So we get 156 minus f of 2 is 136. I need to move this again. And remember, you can speed this up if you need to, over 3 minus 2. So that looks like about 20 over 1, positive 20 over 1. So at this particular point in time, and we don't really need this, so I'm going to minimize it. We do see it's positive, it's going up, and it's about 20 feet per second. We could probably have gotten it. They don't give us a good values, easy values to see, but this is what this looks like, about a 125, that's 150. Yeah, it looks about accurate. Okay, yeah, 156, 136. So it's 20 feet per second. That's average rate, average velocity. But what is the instantaneous at 2 seconds? Well, this is where I'm going to show you how we could use the calculator, as well as how we would calculate it. Let me go ahead and no, I'll leave that. I don't want to take all that off. Okay, so since we have the graph, we have y equals, we can go to the graph. Now, it's at 2 seconds. We know from our table that it's going up as high as 156. So to be able to see all of this, we'll adjust the window so that the y max is like 160. We'll go back to the graph. There it is. There is a function, so we're going to go second calc. Notice calc is above trace. And I know I'm sometimes not looking at the right place, but what they've got this dy dx, and that's the other form of the derivative instead of f prime. This is the other way to write it. So that is actually the derivative. So we come down to number 6. We want to calculate the derivative. We've got to give it a point, and the point we want it at is 2. We're going to enter that, and it tells us the derivative when x is 2 is 36. The instantaneous rate of change is 36. Now, we could have also done that with the difference formula. Casio has a similar feature. The other thing that's going to be nice, I want to show you right now, is we can actually draw the tangent line here, and it will give us the equation of the tangent line. And again, the Casio will do this as well. So there are some homework problems that ask you for the equation of the tangent line. So I'm going to show you how you can do that. Now that's a function that resides here under draw. So I think it's the program key. So since we're here, we go second and we go to program, which is draw. And it asks us, what do we want to draw? We want to draw the tangent line. So we go down to tangent line. We hit enter. And it's just flashing there, but what it's asking is a normal float. So when it's flashing, it's usually asking us for something. And what does it want? It wants the X value. So we put in 2, and watch what happens this time. It'll give us the derivative, yes, but it will also give us the tangent line drawn in there, and it gives us the equation of the tangent line. Now we have to be a little bit sharper here because we see that the slope of this tangent line is 36. We have to know that that means that's what the derivative is. It's 36. It's the slope of the tangent line. But on the questions that ask us to come up with the tangent line, this is one method that will get it to us very, very quickly. The other way is to take the 0.2 comma 136, which we had, and then use to find the linear equation. Again, I'll do that a little bit later, but I'd like you to at least get some proficiency for those who have a TI-84 calculator. Those who have the Casio, there's a similar, and I found out how to do this by doing a little search, and they've got videos on them as well. And maybe that's what I'll do in the initial, is I'll just build a resource of other people showing you how to do these. And then I'll do it myself as I get more time. Okay. So let me shrink this down. So what we've done here, we've done several things, but we're still able to find average velocity, average rate of change, as well as instantaneous rate of change. We're using our technology. And as the book is even telling us, when we use the technology, we were using a built-in balanced difference quotient, okay? And we have done them by hand before. We were just doing it the previous day, so it'll be the same technique. And again, what we would have done here is we would have found the linear equation where the slope was 36, and it went through the point 2 comma 136, because that's what we figured out. We had to find that. So there's a slope and a point. Now you could use the point slope formula. You could also use the y equals mx plus b. Let's see, the slope point is y minus y1 is equal to the slope x minus x1. So there's this formula here. You can plug in your where x1 would be 2, y1 would be 136, and the slope would be 36. So that's another way of getting the tangent line, but with all of these methods would get us to 136x plus 64. Okay, so we're going to clean that off. Okay, what I want to do now, this is the 10.5 homework, so I just kind of want to go through. And this one, there's nothing for you to do with the calculator or anything else. It's giving you this table of values, and it's giving you the average rate of change over from 9 to 9 plus h. So up here, h is getting closer, is getting smaller and smaller. The distance from 9 to that next point getting smaller. It starts out 9 to 10, right? That's this point here, or 9 to 8. It's actually coming from both directions. So it's using this balanced approach. But we see as the distance between the 2 points becomes smaller and smaller, our rate of change, our instantaneous rate of change, is going towards 6.5. Around this is 6.5. So your numbers will be different, but that's what this table has everything you need. Yes, it's just as simple as time to write in here. Sorry, I was on the wrong side. To write in here is 6.5. Okay, so that's what's happening here. The next one, and what I'm going to do is kind of just go through here. They give you a graph of a function, and they give you the point of tangency, and it's not really easy to see what that point is, but what we can do is we can estimate the slope of the tangent line, which is what they want. Graph of function, give its tangent lines, go up a little bit more, estimate the derivative of the function at this point. And again, that just means find the slope of this tangent line, and it looks like it's going through 0, 0, so that's usually a good point to use. And then it's going through 3, 9. So I would use 0, 0 and 3, 9. Again, it's red. Your line may be different. The point might be different, but we're finding the slope of the tangent line. Now, this is not a secant line because we are using the tangent line itself. We are not using the 2 points on the function. This is the slope of a tangent line. So as we subtract these 2 points, it looks like we'll get -3 over -9, which is, we get -3 here, we get -9 here. And then remember, the x goes underneath the y. So it looks like it's going to give us a slope of +3. And it should be positive because it's increasing. So that's how you'll do yours. It'll be slightly different, but find 2 points and you'll start to see these. Now this one, again, we've got the tangent line, and again, choose 2 points on this tangent line and find the slope of that tangent line. And that will be the derivative, okay? We can estimate the derivative by looking at the slope of the tangent line. And negative numbers are smaller than positive numbers. It cuts off here, and negative numbers are less than 0. So I can see right here, see P, if I draw that tangent line, right, it looks like the slope is 0. And then when I draw the tangent line through Q, it's going to be negative, and it looks steeper than when I draw it through R. Okay, so, this point is going to be steeper than that one. So you can take your guesses that way. The most negative slope is going to be the smallest rate of change. So -7 is less than -5. So the steepest negative is going to be the smallest instantaneous rate of change. Zeros and positives will be the greatest. Okay, so give that one a try. To do a quick approximation, again, what I would do with this is I would graph this. I would put this in my y equals. And I don't know why this is, but I would put that in my calculator, graph x over 5 minus 3, and I would use that derivative tool. And again, I can help you locate that with the Casio. Do the derivative 2 at -3, and that will be your derivative. You can also use either the balanced or the other difference quotient. So we would use f of -3 plus h minus f of -3 all over h. And we take the limit as h goes to 0. Okay, so that would be your approach for number 5. And for number 6 here, again, you could use any method, and that's the key part, any method to estimate the slope of the tangent line till this one. So again, you could use the graphing calculator, have it find the slope at that point for the tangent line. And then also, as I showed you earlier, you can use that feature to actually find the equation of the tangent line. Otherwise, the slope that you came up with here, the derivative, remember the derivative of any function at that point is the slope of the tangent line. Okay, so you would take that slope and you could use y minus y1. I think this is the point slope formula from algebra. X minus x1. Plug it in, you'll get your equation, or use the graphing calculator. Okay, and then you would, the advantage of using the graphing calculator, it makes it a lot easier to figure out which graph to get to pull up. And again, with this one, we're doing it at x equals -1. So hopefully you can see that this is x at +1, so this couldn't be it. This is possibly it because it's x at -1. That's where the slope is going. Or it could be this one. So there's two choices. There's two obvious wrong choices because this is at x equals +1. Again, there's reasons why they show that one. So it's not that it's, there are reasons why people might, flip the sign and come over here. But it's one of these two. And if you use the graphical approach, you'll be able to match it up quite easily. Use any method to estimate the slope. Again, any method. You can use the estimation with the difference quotients. You can use the graphing calculator. And again, the advantage of using the graphing calculator is you could also use it to find the equation of the tangent line. It will give it to you. Okay. And then again, you're choosing it. So using the graphical means gives you the first answer, the second answer, and it also gives you the graph. So you have it all three in one fell swoop. And again, I'll post a little video on how to do it with the Casio, or at least a link to it that I've used. And then we're given this function as a graph, and we're asked to determine whether for which x is the function decreasing. So x is the function is increasing from -2 here. So we see it keeps increasing until what point? Well, it looks like right there. I mean, this is partially just looking at it. And then from that point, it's going to be decreasing. All right, so this is just following, but it's giving you the idea of what the slope would be, what the derivative would be, the sign of the derivative. So the sign of the derivative for everything from -2 to -1 is going to be positive. The sign of the slope, the derivative, slope of the tangent line and derivative are the same thing. It's going to be negative because it's going to be going downhill on this side. Uphill, positive slope. Downhill, negative slopes. Okay. And here we go. Math books always seem to deal with prison populations, and for those of us who are from communities of color, I find these difficult to even have in here, but here they are. Maybe someday we'll see talk about rising prison populations change when we actually get a government who will address the social inequities, the systematic racism and oppression of peoples of all kind, starting with women, ethnic minorities. Anyway, a lot of things need to change, and I think we could talk about a lot of math type problems without coming to prisons. But for some reason, I find math books always wanting to talk about prison populations. Again, they don't see it because if you're in the privileged class, you don't know people in prison, maybe. Sorry to get on that soapbox, but I just think it needs to be mentioned. Okay. So again, you can see over which time periods in this curve it's increasing everywhere. It's actually increasing, but it's actually, whereas it's more steeply increasing. So over the period 5 to 10, the instantaneous rate of change of n is increasing. Yeah, that's true. From 5 to 10, the instantaneous rate is always increasing. Now, actually, it starts to level off. It starts to slow down here. So it certainly isn't decreasing, but it's an increasing rate, but the rate itself slows down. It's increasing, but it's at a slower rate. So kind of go through these. And again, I'll be happy to discuss these. Population was increases fastest around what year? So what you're looking for is about what year would have the steepest slope. And this is, as we'll see, this is kind of, it's looking like a concave down to a concave up. We're going to look at something called an inflection point where it switches. And oftentimes that inflection point is the place of quickest change as well. So we'll get into those. Velocity, that's okay. Speed, that's, I don't know. I think we all like speed, at least maybe we, it's fun to go fast, I think, but not too fast, right? Okay, so we can look at the average velocity from 1 to 3. So we've talked about this. We've got our function. We find out the y value at 1, the y value at 3, and then we just use the slope formula because it's a slope of a secant line, 2 points. To get the instantaneous velocity at time 3, again, I would use the calculator. Plug this in, use the calculator's tool, because remember, the calculator tool, what it's using is that two-sided, the balanced approach to finding the limit. It actually has it programmed in there. So again, I would use that and keep moving forward. And it looks like we're done with the homework. So I'll do the same thing with 10.6. I'm going to make up that PowerPoint next, do a video on it, and then I'll review the homework of sort of how to get each problem started. And hopefully that will keep you moving through the weekend so that we can get through this content at least by next Friday. So we have a weekend and one whole class period where we can go over the practice tests and the concepts and see how they're all interconnected, because that's really where, to me, the learning begins, is where we've learned all these pieces, but when we go to study for a test over a unit of study, what we get to do is we get to bring all those pieces together. Some of those early pieces we've replaced with easier ways to do it, and we will. But that's where the real learning and connecting happens. So anyway, I'll let you go now. I'll make up the next video and get that posted as soon as I can. Thanks.